we have two aircraft here. We have a propeller-driven aircraft and a jet aircraft. So with the propeller-driven aircraft, we are told it's taking in air at 250 kilograms per second, and the aircraft is flying at 10 meters per second, and the jet stream is 16 meters per second. With the jet aircraft, we're taking in 50 kilograms per second. The aircraft is flying along at 50 meters per second, and the jet velocity is 80 meters per second. And let's work out the thrust. Okay, so if we take the propeller aircraft first, so the thrust is the mass flow times Vj minus Va. So the mass flow is 250 kilograms per second. The velocity of the jet is 16 meters per second. The velocity of the aircraft is 10 meters per second. So that gives me a thrust of 1.5 kilonewtons. For the jet, we have a mass flow of 50 kilograms per second. The jet velocity is 80 meters per second, and we were told that the aircraft is flying at 50 meters per second. So that is also 1.5 kilonewtons. So we've equal amount of thrust from both engines. Okay, so what if both are at rest? And what is the kinetic energy in the air? Okay, so if they're both at rest, then the velocity of the aircraft is 0. So we get 250 times 16 minus 0, which is 4 kilonewtons. And over here we get 50 times 80 minus 0, so the aircraft's at rest, and also 4 kilonewtons. So again, equal amount of thrust. Okay, so the kinetic energy in the jet. Okay, so kinetic energy is half mvj squared, or it's half mv squared. Okay, so it's going to be the velocity of the jet here. So it's half, well the mass was 250, the velocity is 16, so that's 32 kilojoules in this scenario. Okay, so the energy of the air here is 32 kilojoules. And the energy of the air here, well, it's half mv squared, so it's half 50 kilograms per second by the 80 meters per second, and that's 160 kilojoules, so 5 times larger. Okay, so there's 5 times more energy in the wake of the jet aircraft than there is in the turboprop aircraft, even though they're both producing the same amount of thrust. So what does that tell us? Well, it tells us a lot actually. If we go back to the law of conservation of energy, we're told that energy can't be created or destroyed, just change from one form to the other. So if we take the piston engine aircraft here, it has 32 kilojoules of energy. Now it was at rest. Okay, so the engine was at rest. If I just go back to this slide here, okay, so it was at rest. 4 kilonewtons of thrust, and we saw that the wake was 32 kilojoules of energy. So if I calculate the energy of the air here, okay, the aircraft's at rest, so there's no energy in the air here, whereas out at this point here, it has 32 kilojoules of energy. So where did it get that energy from? Energy can't be created or destroyed, just change from one form to the other. And where it gets its energy from is the fuel. Okay, so we need to burn fuel to give this energy. So it got this 32 kilojoules of energy from the fuel. If we look at the jet engine, again it was at rest, and it has zero kinetic energy here, whereas out the back we just calculated that it had 160 kilojoules of energy. So where did it get that fuel, or that energy? It got it from the fuel. So what this tells us is that the turboprop engine is more efficient in terms of fuel usage, because we don't get a lot of fuel wasted out the back all this energy is wasted. It's gone out the back. So we burnt fuel to get that energy. So by using a turboprop, we would have a more fuel efficient energy. And just to highlight that again, so here's the engine. So it's 32 kilojoules of energy here in the wake, 160 kilojoules of energy here. It can only get it from the fuel. If we consider that the heating value of fuel is roughly the same, that means we would have had to burn 13.3 kilograms of fuel an hour for this amount of energy, where the mass here is 2.6 kilograms of fuel per hour here. So this is obviously more advantageous, and this was cost us more money. Okay, so now the problem with piston engines is, they're limited in the height, and their reliability isn't as good as jet engines or turboprop engines, and they're limited in their height and so on. But if we can use an engine that accelerates a larger mass of air by a less amount, then it will be more fuel efficient. And what engine manufacturers have done is they've taken the turbojet and they've stuck a fan on the outside of it, so it's a bit like a big propeller. It's generally, well, it's inside a duct, so we get air going through the fan. So we get a large mass of air, and that's accelerated by a small amount, and that improves the fuel efficiency of the engine, and that affects the cost for the aircraft operator. I would say that about between 40 and 48% of an airline's expenditure is down to fuel. So if you can reduce your fuel spend, you will have a big impact on the bottom line of the company. So you'll see that engines now are moving to these turbofans, and the bypass ratio, basically the size of this is getting bigger and bigger. I mean, it was 5 to 1, 8 to 1. It's now up at about 12 to 1, just due to the greater fuel efficiency.